Okay, so now we're going to do some more of those heat problems. We're going to start here at number 2. It says how much heat energy is released as the substance freezes. So when you see the word freezes, you know that that means going from a liquid to a solid. So that is this portion of the graph up here at number 2. However, to freeze something means it is going to lose energy. A liquid going to solid. Solids have the least amount of energy, and so that energy is leaving the liquid for that solid to form. Energy leaving that liquid means that it is an exothermic change because heat will be released. Okay? Just like in the Orange Grove article. Because I'm only freezing the substance, and again, that's the 50 grams of this unknown substance. The only equation I need is Q equals mass times the delta H of fusion. So 50 times the delta H of fusion from the table is 555.8 joules per gram. So 50 times 555.8 on my calculator is 27,790. Now, if this is an exothermic change, my heat of fusion, this is how much energy it takes to melt the ice. So flip the sign. That's the amount of energy it takes to freeze that substance. And so that negative makes this answer negative 27,790 joules of heat being released. Right, we got that key word there, released, as that substance freezes. Okay, number 3 is really long. It's the longest kind of question you can find because this one says how much heat energy is absorbed as the substance goes from 40 degrees to 120 degrees. So for this substance in particular, at 40 degrees, it is a solid. So you can see that here on the graph, right? So at 40, we are in that solid state on the heating curve. So step 1, I'm going to have to increase the temperature of that solid until it gets to 50 degrees where it melts. After that melting process, I then am going to raise the temperature all the way till it starts to boil, that liquid going from that melting all the way to boiling at 110 degrees. Then I will need to completely evaporate, boil, vaporize that substance. And then we're ending at 120 degrees, so then we also need to warm up that gas to get to 120, right? That's where we're ending this problem. So to go from 40 to 120, there won't be one temperature change. There's actually, because each of these specific heats are different for each phase, we're going to have to do 1, 2, 3, 4, 5 equations. Okay, so this is the longest kind of question for heat problems. Okay, so I'm going to move this down here and zoom in a little bit so you can see that a little better. So in, I'm just going to call it Q1, right? So for Q1, I know that I have that substance in the solid state, and I have to heat it up. So Q equals mc delta T. Again, the mass for all these substances for this page is 50 grams. Knowing that Q1 is in its solid state, I'm going to make sure I pick the right specific heat capacity. As a solid, the substance has a specific heat capacity of 1.76 joules per gram degree Celsius. So I'm going to use that solid specific heat capacity here. And then the change in temperature, I'm starting at 40, but it's only solid until it starts to melt at 50. So this is going to be 50 minus 40. That is only a 10-degree change. So 10 times 50 times 1.76, that equals 880 joules to warm up that solid. In Q2, we are then going to melt that solid into a liquid. So in melting, Q equals delta H of fusion. We did that up here in number 1, so it's the exact same math. 50 times that heat of fusion gives me 27,790 joules. For Q3, I'm then going to warm up that liquid state. Okay, so because I'm warming and I'm going to have a change in temperature, that goes back to Q equals MCAT. 50, I need the specific heat because I'm in the liquid state here at step 3. I'm going to use the specific heat capacity of that liquid, which is 2.08. And then my change in temperature is only the change in temperature of the liquid. The liquid it melts at 50, so I have liquid at 50 here. I'm going to warm it all the way up to 110. So my temperature change is the 110 minus the 50, final minus initial. 50 times 2.08 times that temperature change is 6,240 joules. Okay. Then in Q4, we have to vaporize the substance. So M times delta H of vaporization, the mass doesn't change. Mass is conserved. But the delta H of vaporization, again, I know I'm vaporizing because I'm going from a liquid to a gas. That's this step 4. And the heat of vaporization in my table is 1993.2. So 50 times 1993.2 gives me 99,660 joules of heat it takes to vaporize that substance. Then my last Q is Q5. In Q5, I am then going to warm up the gas. So in warming the gas, I'm going to change its temperature. So that's Q equals MCAT. 50. I know that I'm in the gas phase at 110. And I'm going to raise the temperature to 120. So that's just a 10-degree change right here. And the specific heat capacity of the gas is from my table. The gas is 1.34 joules per gram degree Celsius. So 1.34 is my C, and my delta T is the 120 minus the 110. So 50 times 1.34 times that 10-degree change is 670 joules. Once I have all 5 of those Q values, I then add them all together, right? So when I combine all these Q's, 760 plus 99,660 plus 6,240 plus 27,790 plus 880 joules gives me 135,240 joules total. That's how much heat it takes to raise the temperature of that solid unknown substance from 40 all the way to its gas at 120 degrees. The last question is not that long, right? That was the longest one, is doing 5 Qs. The last question has us do how much energy is released, there's another big hint word right there, as the substance condenses at 110 degrees and continues to cool to 60 degrees. So if it continues to cool to 60 and we're at 110, we're going to take the time to step 1, Q equals mass times delta H of vaporization. That's the condensing part. And then in step 2, we'll use Q equals MC delta T to finish cooling it off from 110 down to 60. Remember that as we're releasing and we're condensing, that is going to be the same heat of vaporization. We just have to flip the sign. So the mass is 50. The heat of vaporization is 1993.2. But because we are losing heat, we indicate that with that negative sign. And that gives us negative 99,660 joules. Because our mass doesn't change. And then in step 2, when we cool it down to 60, mass, we have condensed it into a liquid. So when I have my specific heat here, I know that's in the liquid state. And I use the liquid specific heat from the table. And then the delta T, I'm ending at 60, but I started at 110. So 50 times 2.08 times 60 minus 110 gives me negative 5,200 joules. Even though they're both negative, I'm still going to add those together and get a large number. Negative 99,660 plus negative 5,200 gives me a total of negative 104,860 joules. Okay. So now, if you will try your specific heat problems PL on Canvas, hopefully these examples help you.